Principles of Communication subject introduces theories in the area of communication systems. Topics covered include the basic elements of communications, signal analysis, amplitude modulation, angle modulations, and digital modulations, as well as transmission channels and noise impact on the modulation system. The effective communication system is one which achieved its objectives. Communication is effective where there are no barriers to communication. The message should be clear and complete. Oscillators and filters play important roles to achieve this. Oscillators lie at the heart of many electronic and communication systems that depend on accurate time measurement and coordination. They are used to stabilize time frequency generators, which in turn provide carrier and pilot signals for electronic communication and navigation systems. A filter, on the other hand, is a circuit capable of passing or amplifying certain frequencies while attenuating other frequencies. Thus, a filter can extract important frequencies from signals that also contain undesirable or irrelevant frequencies. We were assigned to do 7 experiments regarding principles of communication system. Specifically, they're about oscillators and filters. In this video, we will discuss each one of them. Let's start with the first one. Our first experiment is about RC phase shift oscillator. Oscillators are circuits that spontaneously generate a periodically changing output voltage due to positive feedback. Two important types of them are Wien bridge and RC phase shift oscillators. The RC phase shift oscillator uses 3 cascaded stages of RC high-pass filters with the output of the last stage feedback to the inverting input of the operational amplifier. The purpose of constructing RC filters is to provide a phase shift of 180 degrees. Since the output of these filters is feedback to the inverting terminal, the amplifier itself provides another phase shift of 180 degrees. The total phase shift of the circuit is therefore 360 degrees or 0 degree. For an oscillator to sustain oscillations indefinitely, sufficient feedback of the correct phase, that is positive feedback, must be provided along with the transistor amplifier being used acting as an inverting stage to achieve this. An ideal single-pole RC circuit would produce a phase shift of exactly 90 degrees, and because 180 degrees of phase shift is required for oscillation, at least 2 single poles must be used in an RC oscillator design. We therefore conclude that because of the characteristics of the RC phase shift oscillator, it can be used for low frequency generation up to few hundred of kilohertz. Typically, it is used for the audio frequencies. Our second experiment is about low-pass filter. A low-pass filter is a circuit that can be designed to modify, reshape, or reject all unwanted high frequencies of an electrical signal and accept or pass only those signals wanted by the circuit's designer. In other words, they filter out unwanted signals, and an ideal filter will separate and pass sinusoidal input signals based upon their frequency. In low-frequency applications, passive filters are generally constructed using simple resistor-capacitor networks. Passive filters are made up of passive components such as resistors, capacitors, and inductors, and have no amplifying elements like transistor, op-amps, etc. So they have no signal gain. Therefore, their output level is always less than the input. A simple passive RC low-pass filter, or LPF, can be easily made by connecting together in a series a single resistor with a single capacitor, just like in our experiment. The bode plot shows the frequency response of the filter to be nearly flat for low frequencies, and all of the input signal is passed directly to the output, resulting in a gain of nearly 1, called unity. By carefully selecting the correct resistor-capacitor combination, we can create an RC circuit that allows a range of frequencies below certain value to pass through the circuit unaffected, while any frequencies applied to the circuit above this cutoff point to be attenuated. Our third experiment is about second-order Butterworth filters. The shape or width of the roll-off, also called the transition band, for a simple first-order filter may be too long or too wide, and so active filters designed with more than one order are required. These types of filters are commonly known as the high-order or nth-order filters. For a filter that has an nth number order, it will have a subsequent roll-off rate of 20 ndB per decade or 6 ndB per octave. So, a first-order filter has a roll-off rate of 20 dB per decade or 6 dB per octave. A second-order filter has a roll-off rate of 40 dB per decade or 12 dB per octave, and a fourth-order filter has a roll-off rate of 80 dB per decade or 24 dB per octave, etc. Our experiment, which is the second-order Butterworth filter, is a type of second-order filter which is simply being the two first-order filters cascaded together with amplification. In applications that use filters to shape the frequency spectrum of a signal, such as in communications or control systems,
The next experiment is about high-pass filters. A high-pass filter is an electronic filter that passes signals with a frequency higher than a certain cutoff frequency and attenuates signals with frequencies lower than the cutoff frequency. This experiment shows a simple first-order high-pass filter implemented by placing an input voltage across the series combination of a capacitor and a resistor, using the voltage across the resistor as an output. We use the formula 1 over 2 pi RC to get the cutoff frequency, where R is equal to the resistance and C is equal to the capacitance in farads. Based on the data or the Bode plot, at the negative 3 dB point, the signal is allowed to pass. This negative 3 dB denotes cutoff frequency. One of the many applications of high-pass filters is that they are used as part of an audio crossover to direct high frequency to a tweeter while attenuating bass signals which could interfere with or damage the speaker. In short, high-pass filters are used to the removal of unwanted sounds near to the lower end of the audible range. This experiment explains bandpass filter circuits. A bandpass filter is a device that passes frequencies within a certain range and rejects or attenuates frequencies outside that range. To compute the center of frequency, we first obtain the low cutoff and high cutoff frequency. Low cutoff frequency is given by 1 over 2 pi R2 C2, where R2 and C2 is the resistance and capacitance of the low-pass filter region of the bandpass. On the other hand, the formula for high cutoff frequency is 1 over 2 pi R1 C1, where R1 and C1 are the resistance and capacitance of the high-pass region of the bandpass. In a bandpass filter, there is a low-pass region where we obtain the low cutoff frequency and the high-pass region to obtain the high cutoff frequency. For our output, or the Bode plot, it is a bandpass of an AM, which is also called a narrowband. Bandwidth is commonly defined as the frequency range that exists between two specified frequency cutoff points. Bandpass filters are widely used in wireless transmitters and receivers. The main function of such a filter in a transmitter is to limit the bandwidth of the output signal to the band allocated for the transmission. This prevents the transmitter from interfering with other stations. The next experiment is about band stop or band reject filter. A band reject filter is a filter that passes most frequencies unaltered but attenuates those in a specific range to a very low levels. It is the opposite of a bandpass filter. Another term for band reject filter is notch filter. A simple band reject circuit is constructed by having a parallel connection of R and C and a series connection of resistor and capacitor. The Bode plot shows that most frequencies are allowed to pass but reject some in a specific range. Band reject filters are commonly used in instrument amplifiers for acoustic instruments to reduce or prevent audio feedback. The last experiment is about Sallen-Key filter. Sallen-Key filter design is a second-order active filter topology which we can use as the basic building blocks for implementing higher-order circuits such as low-pass, high-pass, and band-pass filter circuits. The Sallen-Key topology is an active filter design based around a single non-inverting operational amplifier and two resistors, thus creating a voltage-controlled voltage source or VCVS design with filter characteristics of high input impedance, low output impedance, and good stability, and as such allows individual Sallen-Key filters sections to be cascaded together to produce much higher order filters. This is the Bode plot data of cascaded Sallen-Key filters that is used to implement other high order filter such as low pass, high pass, band pass, and band reject filters. The main advantages of the Sallen-Key filter design are simplicity and understanding of their basic design, the use of a non-inverting amplifier to increase voltage gain. First and second order filter designs can be easily cascaded together. Low pass and high pass filter stages can be cascaded together. Each RC stage can have a different voltage gain and replication of RC components and amplifiers.
Thanks for watching! If you'd like to know more about principles of communications, we highly recommend that you should check the books of Tomati, Blake, and Frenzel, or check the Google website of electronics tutorials and also the website of All About Circuits. Bye!